Low Earth orbit telecommunications promise ultra-low latency by bringing hardware closer to the ground. But that proximity introduces a severe engineering problem: staggering orbital velocity. Ground receivers have to catch a target that refuses to sit still. Take the Starlink Shell 1 deployment. These satellites operate at a relatively low altitude of approximately 550 kilometers above the Earth's surface. At that height, atmospheric drag and orbital mechanics demand a blistering velocity to stay aloft, roughly 7.8 kilometers per second. Managing this network architecture requires shifting from fixed-point infrastructure to a continuous, high-speed tracking solution. Because the routing hardware is constantly moving, LEO networks inherently create a crisis of continuity. The nodes you rely on to route your data are perpetually falling over the horizon. To see exactly how this impacts ground infrastructure, we can look at a specific case study engineered at Tafila Technical University in Jordan. Stationed at latitude 30.83 degrees north and longitude 35.60 degrees east, this receiver sits under a highly active orbital corridor. Any fixed receiver has a local horizon, a narrow, mathematically defined window of visible sky where a line-of-sight signal can be caught and maintained. At 7.8 kilometers per second, a single LEO satellite will slice across this entire viable cone in just 5 to 10 minutes. The primary objective of the Tafila project is to build a high-fidelity 3D simulation to test a specialized protocol, one designed specifically to prevent data drops during these rapid orbital transitions. Traditional network routing relies on hard switching, dropping one connection before establishing the next. Under a strict 5-minute operational window, that method results in continuous outages. A highly specialized routing logic is required. Before any routing protocol can be executed, the ground station requires highly accurate, predictive tracking of the incoming constellation. Standard network systems typically achieve this by pinging third-party API endpoints to request the latest location coordinates. Relying on external APIs introduces a fatal vulnerability. External calls are constantly subjected to unpredictable network latency and strict institutional firewall constraints. When your target is moving at 7.8 kilometers per second, a network delay of just a few hundred milliseconds equates to several kilometers of physical tracking error in the sky. The incoming data arrives as two-line element sets, or TLEs. These are raw, densely coded text files containing the pure mathematics of a satellite's orbit. This localized parsing engine provides the precise coordinate stream required to orchestrate a successful handover. With the constellation accurately tracked, the system applies strict geometric boundaries to the Tafila ground station to execute the transition. The primary constraint is the minimum elevation angle, which is locked at exactly 15 degrees above the horizon. This 15-degree limit models realistic line-of-sight constraints. It ensures the signal path is high enough to clear physical terrain obstructions and dense, low-atmosphere thermal noise. By processing data through both orbital relays simultaneously, the system guarantees zero packet loss. Finally, in Phase 4, the original satellite drops below the horizon and the new satellite takes over. By geometrically overlapping the signal paths exactly at the 15-degree threshold, the protocol successfully neutralizes the extreme velocity of the orbital hardware. This system architecture handles a heavy computational load, executing hundreds of complex 3D orbital dynamic calculations every second. The data logs confirm the physical handoffs, showing the precise timestamp when the ground station shifts from one specific node, like Starlink 45669, to the next. The logged connection durations, often lasting precisely 5 minutes and 40 seconds, or 6 minutes and 20 seconds, verify the strict operational window dictated by the orbital mechanics. But the Tafila case study successfully rendered a complete 4-phase handover across Jordan's local horizon without a single instance of network downtime. That seamless transition relied entirely on stripping away third-party APIs and computing the physical geometry inside the local machine's memory. When applied to the broader Starlink Shell 1 deployment, the math scales to govern thousands of satellites interlocking across the globe. The simulation proves that the LEO coverage gap is a problem of predictive geometry, solvable through a more robust data architecture. Orchestrated through a make-before-break protocol, the staggering velocity of the constellation becomes a stable, invisible relay for the ground station below.